What's up, bitches? Today we're going to learn how to find the state variables for a problem like this. The first step is you want to draw your free body diagram. So here's our mass. Next, we are going to draw our input force, which is just Fa heading down. Next, we're going to draw our inertia force, which is always acting opposite to the motion. So since it's here, we could see the x and even the v that is pointing down. So our inertia force is going to act opposite to that. So m times the acceleration, which is, x dot dot. Next, since this is a vertical system, we have our gravitational force, mg. And lastly, we have our spring and damper. The spring force is equal to the spring constant, k, times the distance from the spring, x. Almost like 90% of the time, a spring is always going to pull objects towards itself on problems like this. Not always, but most of the time. And finally, we have our damper system, which is equal to the damper constant times the velocity. So this is our free body diagram. Once we have this, we can begin to draw our equations. So we're going to put whatever is pointing down equals to whatever is pointing up. So whatever is pointing up is the mass, or this is the inertia, plus the damper, plus spring constant, equal to whatever is pointing down, our input force and our gravitational force. Okay. Next, to find the state variables are just like the least amount of variables you can use to describe an equation, but you don't really need to understand that. All you need to keep in mind is that like almost every time the state variables are going to be the motion, or sorry, the displacement x and the velocity. Think of it in a way where you could only describe the system using like one of these derivatives. For example, you can't use x like dot dot. We'd have to use v dot, and that's the maximum derivative you can use to describe the system. So we're going to set these as our state variables. We're going to say that, and then you have to define the state variable's derivative. So the derivative of x dot is equal to the velocity. And now we're going to solve for v dot, which is the acceleration. So this would be our v dot. So mv dot plus bv plus, we're still allowed to use x, equals to fa plus mg. So then, solving for v dot, or the acceleration, you would get the following. 1 over m. You have the input force plus mg. And then you're sending these two things over here to the other side. So you would get minus bv minus kx. And there you go. You have your two state variables here and here. Easy peasy, easy A. So for our last example, we're going to use an example where there's two masses, and we're going to solve this problem by finding the variable state equation. So when you have two masses, the first step is to draw the free body diagram, but you always want to pick first the body where there's the input, which in this case, it's the displacement of x2. Usually you would have f, but in this specific problem, I don't know why they wrote x2, but whatever. You want to always start with this, just because it simplifies things. So instead of writing x2, I'm just going to write fa as the input force. Since it's moving to the right, as seen from x2, the inertia force is going to be acting the opposite direction of that. So m2 x2 dot dot. Then, for the spring and damper, well, look, let's start with the damper, okay? Whenever the damper is connected to two moving bodies, just pretend like this body is stationary, like it's just a wall. Then it would be the damper force would be equal to B and the velocity of x2, right? But since this is also moving towards the right, that's gonna, like, it's not gonna go all the, I don't know how to explain it, bro. It's just not all gonna go all the way, right? So it's gonna be x2 negative x1. Okay, it's just common sense, man. Same principle with the spring over here. Just pretend like this object is stationary. Then that, in that case, as this goes over here, the spring is just gonna, you know, stretch and pull it back. However, since this is also M1 is also moving towards M2, that's gonna, like, make the spring less stronger. You know, it's gonna make it less stretched because it's moving towards it. Okay, it's just common sense. I don't know how to explain it, man. x2 negative x1. There you go. This is our first body diagram. Second free body diagram is we're going to use the M1. Since we have already these two equations over here for the spring and damper, it's going to be the exact same force, but when you're viewing it on a different body, it's just going to be at the opposite direction. Since here on M2 it's acting towards the left, they're going to act towards the right over here. Exact same thing. Whoops. Okay, 2 x2 negative x1, and then damper, same thing, b x2 dot negative x1 dot. God damn, sorry guys, I'm writing with a fucking mouse, it's impossible. Since this object is moving towards the right, hold on, let me clear this shit out. Since it's moving towards the right, its inertial force is gonna act opposite direction to that. M1 x1 dot dot, which is the acceleration. And then finally k, like I said, 90% of the time it's gonna, like, pull objects towards itself. But in this case it's like connected to a wall, so as this is moving towards the right, it's gonna stretch and pull the object back. So this is like 100% pointing towards the left. K1 x1. And that's it. So now we can write our equations. What you want to do is whatever is on the left side is equal, you're going to write equal to whatever is on the right side. Same thing over here. Whatever is on the left side, you write equal to the right side. I'm just going to skip because I'm, like, writing with a mouse, so I'm just going to type it out for y'all. Just hold on, give me a second. Okay, here we go. I typed it out for y'all. It's over here. Squeaky clean. So as you can see, whatever's on the left side, M1, X1 dot dot, whatever, it's all over here, equals to whatever's on this side, over here. And same thing with this second free body diagram. So let me just, now that we have that, you don't really need the free body diagrams anymore. I'm just going to erase it to make room. And on the initial problem. Okay. So, okay, next we could write our state variables, and while taking this class, literally, like, every problem, the state variables were always like x1, v1, okay? So when you do your exam or your problems, always start with these, because this is normally how it's going to be, the state variables, x1, v1. Sometimes when there's a second mass, there's also x2, v2, but in this specific case, our input is x2, so you can't really have that as your state variable. So, these are our state variables. The next step is you have to define the derivatives of your state variables. x1 dot is just equal to the velocity, and v1 dot, we're gonna use this equation to find v1 dot. So we're gonna send this to the other side. v1 dot, by the way, is just the acceleration, which is this over here. So we're gonna isolate x1. I'm just gonna skip and do it all over here like this. v1 prime, which is equals to x1 dot dot, by the way, is equal to 1 divided by m1. And then I'm just going to distribute everything. bx2 dot negative b x dot 1 is x1 dot is just v1 plus k2 x2 negative k2 x1, my bad, negative k1 x1. Beautiful. Now there's a problem over here, okay? When you're defining your state variable's derivative, on the left hand side you can't have another derivative. In this case we have x2 dot. You can't have that. Like normally, and we can't even write v2 because x2 is your input. So you can't really just like change it however you want. You have to consider this as x2 dot. So whenever you have a problem like this, all you have to do is send this shit to the other side. Okay, so it's going to be v dot 1 negative, keep in mind that there's this m1 over here, so there's going to be b divided by m1 x2 dot. Now we have to consider this as a new state variable because when we bring this to the other side, everything is good. There's no more derivatives. So next step, hold on, let me create some space. Watch this shit. There you go. Okay. Now, you can't just set this as a new state variable q. You can't exactly do that. You have to consider like all of this as like q prime. We're gonna set a new state variable called q, and we have to define this without using derivatives. So it's just gonna be equal to v1 minus b m1 x2. I don't know what happened with this fucking note 1 shit. So ass. There you go. What? Come on, man. What a shit app, bro. Fuck Microsoft. Anyways. So, we have to define our new state variable. So with this, we're going to isolate v1 because you still have to define x1, right? These are our original state variables, but we just have to like redefine them because of that derivative. So v1, we just send this shit to the other side, is equal to q plus b divided by m1 x2. So rereading our state variables, we can't really say v1 because now we have to use q. We can't really use v1 prime because it doesn't work. So x1 dot, we could still keep x1 because it's fine, is equal to v1, and v1 is equal to this, so you're just going to write that is equal to q plus b over m1 x2. Next, since we're not using v1 anymore, we are using q. So now all that's left is to define q prime, which we know is equal to this. If we right, this is normal q, and q dot is just the derivative of all this shit over here. So we're just gonna replace that. Let me just fuck, man. Hold on, let me just make some room. There you go. So since you brought all this shit to the other side, it's just gonna be the q prime is just gonna be the exact same shit, except you're just ignoring this because we brought it at the other side, right? So q dot is equal to 1 over m1 negative b v1 plus k2 x2, and I'm just gonna distribute the x1, like I'm gonna factorize x1, and so that would give you negative x1 k1 plus k2. And there you go. That is your state variable. The answer of this question, state variables, would be, well, these are your state variables, and Q1 is equal to all this shit that we wrote. That's it. Easy peasy. So thank you for watching. Subscribe. Bye.